Okay, we are ready to start. Welcome back. So today we have 3 presentations. But before the presentations, let me remind you that we have about 10-15 minutes for questions at the end. Those that are online, you can put your questions on chat. Please remember to turn off your cell phones. And finally, so we're going to have a small issue. Anyone who wants to use data, as knows what issue is. And if you don't, you're doing something wrong and say that. So we're going to have Mauricio. It's going to be the first one. Then we're going to have Miguel Nelson from the University of Media, and finally Yanni Cultura from the European Central Bank. So without further delays, Mauricio, please start.
Right, so my presentation is going to be about how to work efficiently with big data sets in Stata. I am a PhD candidate at Brown University, and throughout my years there and before that for several years, I've been working with large healthcare data in the United States. And I work in Stata with this data, and I coded some Stata packages, and I somehow become known, I guess, through that. To give a presentation on that, and I'm going to talk with you about how I think of working with big data. And you organize your project, you have ideas of how to automate things, but then you sit down and you have to write a do file, and then you're going to encounter some issues with big data. And I'm going to talk about that today and how at least I think through solving them and making my life easier with Stata. Okay, so why is big data different? Well, scale, I think scale matters for a couple of reasons. And maybe is the first thing that comes to mind, certainly for me. An operation maybe takes a second with 10,000 observations. If you scale that up with 100 million, suddenly it's taking hours. And then what do? You run a simple command. You're not going to sit in front of your computer waiting for it to change, right? Like you need something more efficient. Second is memory. I think this has been touched upon a little bit. Again, with the small data set, the variables are 4 or 8 bytes of data. And with 10,000 rows, even thousands of variables, it's a couple hundred megabytes. That fits on any computer here, no problem. You can do anything you want. 100 million, each variable is suddenly, close to a gigabyte. Couple variables, several gigabytes. You have to do some analysis. Suddenly, you're starved for memory. And then what can you do? And then last, some things can break with big data. This is not obvious. I'm going to give you one example. Just sometimes when you're debugging, it's useful to keep in the back of your head. Maybe there's something that went wrong because my data is so big. More often than not, this is not an issue, but sometimes it is. And I'm going to give you a specific example of when that can happen. So I'm going to talk about that. I'm going to talk a bit about memory management in this data. And then I'm going to talk about, for most of my talk, hopefully, on efficient code. So this is the example that I have of something that can break with big data, which is if you're generating an ID to uniquely identify rows, right? So it's not an uncommon operation. Stata's default type is a float, and the float can only store integers up to 2 to the 24. So you can see here, I've generated more observations than that. And after 2 to the 24 observations, it kind of breaks, right? The ID starts to repeat. So then what can you do about this, right? Well, maybe you want to store everything as a double. I think many programs have double precision numbers as default. And then you kind of circumvent this problem, but you double your memory requirements, right? Doubles are twice the size of a float. And Stata tries to be memory efficient by default. So the way that you can generate IDs, anything that's bounded above, like the number of observations in your data, in Stata, is to use this ops_t macro. And that gives you the memory efficient type to store integers, right? And I've coded here a little snippet. You can see what it's doing. The largest long is 2.5 billion observations or so. So you have some ways to go before you actually need to go to 8 bytes, right? Long is 4 bytes, int is only 2 bytes, and byte is only 1 byte. So this is kind of a memory efficient way to store integers, yeah? And again, it has to be bounded above by the number of observations, but there are many cases where what you're generating is. So this is just one example I want to give quickly before moving to memory management. So Stata has many variable types, yeah? And you can see more of that if you type cloud data types, but the largest is a double. This is numbers, this is what many programs use at default. But typically, before you get to a double, you want to store data in memory efficient ways. Stata's default is a float. But integers, you don't want to store in floats. Like I said, it's not very good. Long is the largest integer type. And again, before you get to long, you have int, which is 2 bytes, and byte, which is 1 byte. If you have indicators, if you have tuple categories, you should be using byte. You shouldn't be using anything bigger. If you maybe have dates or counts, maybe go with int. Dates in Stata are a day count from 1960. So we still have a couple decades to go before you have to upgrade from int to long. Right? Int is a memory efficient way to store dates, for example. There's a really great Stata command called compress. It's CPU intensive because it loops through your data, but it recasts each variable, both numeric and string, to its smallest possible type. And I feel like I have 2 anecdotes from last week that I'll talk about today about big data and Stata. It's a bit providential. I've had the biggest success I ever had with compress last week. I got this data set from this data provider, 150 gigabytes. What's in this data? I was supposed to be getting 6 variables. I do describe using data. Yes, there's 6 variables. 4 of them are string variables, 256 character strings. 1 kilobyte per row. Okay, it's 150 million rows. What's in these character variables, right? I didn't think that I was getting, super long descriptions of whatever was going on with each row. So I loaded the first couple thousand rows into Stata, and Stata can do that very efficiently. It stores data by row. So if you're only loading a couple of rows, that can go very fast. And I started having a look, and it turns out that the data weren't actually 256 characters. There were 8 characters, but for whatever reason, the data provider had given me 256 character variables. So I looped through the data set. I think I did like 100 chunks. It took a minute or 2. And I compressed this chunk. I appended it all together in the end. And suddenly I had 5 gigabytes of data, and that's perfectly manageable. Now, before last week, I hadn't had such a big success with compress. It usually saves like a fair amount of data, of memory. But just to show you that you should always be doing this, because sometimes you get really lucky and suddenly you have a lot of memory saved. I should say, if you're familiar with file compression, that's not what this is. I was using this command once, and somebody else was looking at my code, and they were very nervous because they didn't want file compression. This is not file compression. This stores the identical data in memory and in your data set, but it just throws away wasteful space by having variable types that are too big for the data you're storing. If you're storing an indicator variable as a double, that's 7 bytes of data that you're wasting, right? And you shouldn't be doing that. The only reason in Stata not to use compress is if you can't spare the CPU. For whatever reason, you're pressed for time, you don't want to have compress at the end, that's fine. Almost always, you want to use compress with your data. And then the last thing is to organize your data. You don't have to store everything in the same file. If you're pressed for memory, wasting a little bit of CPU time can sometimes be a lot better than wasting the memory, right? If you have a data set and then you do 1 merge and some analysis, then later you do 2 more merges and so on and so forth, that can often be better than doing 5 merges at the start and then having too many variables in memory. Just loading what the data sets you need. And then the last thing is, I want to talk a little bit about encoding strings as numbers, because strings are extremely inefficient. Each string character is 1 byte, like I was just talking, 256 characters, 256 bytes. Strings are very heavy, and you usually don't need them for most analysis. You have categorical data encoded. Work with the encoding at the very end. Once you've done your analysis, you have your table, whatever, then you can decode your strings. But you should never have strings in big data if you can't help it. And I can think of very few cases where you actually need string data in very big data. I'm sure that there's some analysis where you really require it, but for the most part, categorical data can be encoded. And if you want to use value labels in Stata so you can remember what each variable means, that's fine. Stata is pretty good with value labels, but don't store strings raw in big data sets. will really take up a lot of space. Okay, and then the last thing I want to talk about a little bit before moving on to efficient coding is swapping. So I've encountered this a bit because I work mainly in shared servers. And I start a program, it takes a lot of memory, and somebody else starts a big program, and then we're competing for space. I think if you're working on a cluster or something like that, they try to solve this problem by having you request memory beforehand. But if the OS runs out of memory, if you're running a program, your data fits in memory, you're running on operations, maybe they make copies, you turn up variables, whatever. And suddenly the operating system says, I have no more memory to give you. What does it do? Well, it can kill your program, but that's a bit violent, so it tries not to do that. The second thing it does is that it moves your data to disk. And when it does that, more often than not, your analysis will grind to a halt. There are programs written specifically to analyze data on disk. But if the program is not, and suddenly part of its data is on disk, it will be super slow. And sometimes it will just not finish in a reasonable time frame. So what can you do? I mean, you can try and minimize your program's memory footprint. You can get more memory. Yesterday, somebody mentioned this. Sometimes it is the easiest solution to throw money at the problem and buy more RAM, but sometimes you can't. One thing that I have done and I have had some success with is to chunk the program execution, like read data by row, data stores data by row. So reading chunks of data by row can be really good. So the anecdote I have about this is, I had health insurance data, I have enrollment data from 80 million people, I have monthly enrollment, 5 variables over 10 years, that's 600 variables. If you do some quick math, that's billions of rows of data. And I want to collapse that somehow to annual enrollment data. And doing that in one go is probably fast, but I was very nervous, like maybe this can fit on one of the servers, but if somebody starts a program, I will start to swap and this will never finish. So I did, I think, 10 or 100 chunks. And because each individual's enrollment doesn't affect anybody else, I just processed it by chunk, and that was perfectly fine because the memory requirement went down by a factor of 10 or 100, and then it's no issue. So chunking your program execution can be a very efficient way to, if you can do it, right? For data management to save memory, and sometimes random programs will be fine. Okay. So now talking about efficient code and how I think about it. So part of it is, of course, code that executes very quickly, but there's a trade-off, right? Writing code efficiently is slow. Writing code quickly, of course, it doesn't take very long. Now, very often, you want to make your code very efficient. But very often, you're looking at a time investment of 2 days to make a code very efficient, and then you save an hour, but you wasted 2 days. And was that a good use of your time, right? The second thing is, it's always good to plan ahead. I think somebody mentioned this yesterday as well, but if you have a lunch that you have to go, maybe task your long program that's going to take 2 hours for your lunch. If you're going home for the day, then maybe don't run the program that's going to take 8 hours until you're about to go home. Then you press run, and then you go home, you come back the next morning, and it's done. And these types of things. If somebody else has already solved the problem you have, it's probably the case you're not the only person in the world with the problem. You look around, somebody else has already have a solution. Just copy the solution and use it, and you save a lot of time. If a program takes 8 hours to run, but it's going to take you 16 hours to code, it is way cheaper to, again, look for a solution, let that run, and then you save actually a lot of time by using somebody else's code, right? Last thing is, I want to talk a little bit about how sometimes the bottleneck is not the steps that your code is executing. Maybe it's doing that very, very quickly, but the algorithm that you're using is maybe very slow. I think a very good example here, if you've ever had to compute a leave one out mean, so an average where you don't, where you omit the current observation, I don't think anybody here would loop through each observation, say compute the mean without it, and then for each observation, that's the mean, right? I think everybody here knows the trick of computing the sum, subtracting the own observation, dividing by n-1, right? But there are many cases where it's not so obvious how to improve your algorithm. So I want to talk a little bit about that. And again, I have an example from last week where a very simple change to what the person was doing resulted in a big improvement. And then the last thing is to pick the best tool for the job. I somehow know quite a few programming languages, but so I use R, I know Stata, I know Python, I know MATLAB and SAS and Julia, and each of them have their own comparative advantages. Like I've never tried to do web scraping in Stata, for example. I'm not even sure you can. And in Python, it's super nice, right? But I do like my data management and analysis in Stata, for example. So it depends on what you're doing. You're not going to have a single program that does everything that you want. And sometimes knowing when to switch can be a real time saver. Okay, so I like this comic. It kind of exhibits the trade-off between how long you can spend on a routine to make it faster versus how many times you're actually going to do it. So for example, if you're doing something every month, yeah, and you're going to be doing it every month for the next 5 years, how long can you spend working on it before it becomes inefficient? So if you're going to spend an hour, you need to shave off at least a minute of for that to be cost efficient. Yeah. If you're going to only be saving, a second, don't spend the time, right? If you're going to be doing something once a year and you're only going to shave off 10 minutes, don't spend the time. If you're going to be doing something many times a day, it's some process that you have to run over and over, maybe in the background, and you're going to shave off 10 seconds, maybe it is efficient to spend some time doing it because it runs so often, right? So again, thinking about this trade-off is important. You can't just say, yes, optimize everything, let me be the fastest at everything. Your time is really valuable as well. Okay, planning ahead. So for example, if you're going to be doing many operations that are very similar, right? Pre-computing some variables instead of generating them on the fly all the time. If you're going to be doing operations by group, if you're going to be doing many merges, sorting the data beforehand can really help. A lot of commands try to sort data internally, generate variables on the fly internally. If you can avoid that, you can speed up your program as well. And then what I was talking about, sometimes it's inevitable you have a program that takes a while to run. You're working with 100 million, a billion observations. You can be as fast as you want. Sometimes your program is just going to take 3 hours, 5 hours, 10 hours, right? And then planning for that and leaving that running overnight or over lunch or whatever. Again, your time is valuable. It's better for you to leave that running overnight than for you to get in the morning, sit in front of the computer, babysit the code, and go home at the end of the day. That's a waste of time, and you shouldn't be doing it, right? And then the last thing, and this is really important with big data specifically, and one thing I really like about Stata is the log. Logging is kind of inherent to Stata, and you should really use that. You can see the log as the program runs. Usually Stata is running to its log file as it's going, and you should be printing log messages. Having your program execute in parts, you have part 1, you're displaying messages to the log, part 2, displaying messages to the log. Part 1 finishes, you have a checkpoint, you save your data, you move on. If there's a problem, again, this is not the final run of your data. You're writing a do file, you're working on the kinks, you're working on the problems. You can restart from part 2, you don't have to really know what to do that. So, and then if you're in the middle of a program and it breaks and you didn't get to the first checkpoint, but you have a lot of log messages, then you can say, oh, it broke in this particular part. Let me get here and then debug, right? Readily available solutions. If you need to code like high dimensional fixed effects, there's a trick that you can do and you can code yourself, don't do it. RegHDFE is very good, right? And there's similarly available solutions. If you want to code things in parallel, again, you can do it yourself in Stata. You can call many instances of Stata from the command line, but there's a command called parallel that does that for you, and that sometimes it's really easy to use. If you're doing operations by group or doing data management, I coded GTools, and that made it as fast as I can. And again, if you're trying to do something like this in Stata, it's probably easier to do that than to code different solutions. I say probably. I'm happy for you to build something that's faster than what I did. Just tell me about it, right? So I'm going to talk a little bit about GTools, because I think if somebody knows me from Stata, that's kind of what they know. And the reason that I coded GTools, and I think this is the story behind every GTools command, is that I needed to do something, and I found that Stata was slow, so I kind of tortured Stata until it was better, yeah? So I was given a very simple task. I was working for this professor as a research assistant, and he said, can you make this data for me, and then collapse this data? I said, sure. I made the data. It was 400 million rows. I tried to collapse it. It was going to be 30 million groups. At the end of the day, it was still running. I come back the next day, it's still running. So I'm like, okay, this is very annoying. I started looking for solutions. And a bit of credit to FTools and Sergio Correa, because he gave me the idea for GTools. I found that, and that was faster, but it was written in Mata, which is Stata's matrix language. And I had recently written a package, both in Mata and in C for Stata. And I knew that if I wrote it in C, it could be like 10 times faster than Mata. So I was like, I could have very similar ideas and implement something like what FTools does, except in C, and then it will be faster. So that's what I did. And up until Stata 16, gcollapse was several times faster. And in Stata 17, Stata kind of finally said, okay, enough of this. And they made their collapse faster. And now it's rare that, especially in Stata MP, that gcollapse is faster. There is one feature about it, which is that it can automatically merge collapse variables back into memory that gcollapse can do. And that's really nice. Like I said, the original impetus was that I had to collapse variables and merge them back in. So I coded it into gcollapse. And collapse can do that. But if you have a regular collapse and you have Stata 17 MP, you can use the regular Stata collapse. It's pretty good now. But over the years, GTools expanded. Because every time I needed to do something in Stata, I said, well, I can just code it in GTools, add it, and then move on. So that's what I did. So I have a ton of GTools commands now. And if you ever wonder, why is this GTools command here and not some other thing that I use all the time? Well, it's because one time, like 2 years ago, I had to do something, so I added it to GTools, and that's the story behind everything, basically. So here I have an overview of GTools commands that have Stata counterpart. You can see now that collapse is very often slower, that my gcollapse is very often slower. But all my other commands somehow still seem to be a lot faster than their Stata counterparts. And depending on what you're doing, it can be a lot faster. And then you can have a look at this table and some extra features that my commands have. There are some other similar like SSC commands. And again, the story behind this is one time I needed to windsorize my data, and the SSC command was very slow, so I just coded gstats windsor, and so on and so forth. And then there's some other GTools commands that don't necessarily have equivalents, but that I like and that I've coded again because I needed it at some point. And I'm going to talk about some GTools commands that I like and some features that I've written that I find really useful and that maybe you will find useful as well. So this is one of my favorite commands for exploring data, that's gtalk. And this is, one time I wanted to look at a categorical variable. I did tab categorical variable, and it said too many categories. I was very upset, so I coded this command. And this command shows you the most frequent levels of a variable. And then, all the other variables, it just says, you have other variables, and that's okay. Yeah. So this works for any number of categories. So you have thousands of categories, and then you can look at how concentrated the variable is. If I'm exploring new data, I use this command all the time because I don't know what's in it. So, and it doesn't matter if you have many categories or only a few. It will just print the most common ones, and then you can move on. Yeah. greshape. I was talking about this anecdote where I chunked this variable, this execution for like enrollment of 80 million people, and I had to collapse it to annual enrollment. In between, I had to do a reshape. And so I coded greshape. And a really important option actually was this drop miss option, because I had this data wide. Not everybody was enrolled all the time. So I had people who weren't enrolled until like 7th year. I had people who were only enrolled until 3rd year. So when I reshape, this option will drop missing observations from your data. If you're reshaping wide too long and you have missing observations, it can be really inefficient to keep the matrix the same size. You can just drop rows where you don't have any information. So that's what it does. And again, here I have some other options that I have found useful to reshape, and I have more details online. I've tried to make my documentation as detailed as possible. Percentiles, I will say, it seems that Stata wrote their percentiles function to be slow on purpose. If you look at the source file, it has a sort preserve. If you have 1,000 variables on memory, that is really inefficient if you just have percentiles for one variable, because you just care about the percentiles for the one variable. But if you're sorting it, because you need to sort the variable to get its percentiles, for the most part, you're sorting the entire data set. That's not very efficient. So Stata could easily code something that's faster, and I hope they do. But for now, like I've coded this solution, you can do it by group, and that's even faster. And you can run this snippet on your own. Again, it's going to be on the slides, and you can see it's pretty performant. Because again, even if you have tons of variables in your data, it will only read the one variable that you care about. This tab, I think if you only have a couple of groups and your aim is to look at summary statistics by group, right? You don't need to collapse your entire data, right? Because you have 5 groups, 10 groups, 2 groups, 20 groups, you want to look at summary statistics, you just need a printout, right? So tab stat is what you do. But again, I was trying tab stat and it was a bit slow, so I coded gstat instead. And this can be a very fast alternative to gcollapse. This should be faster than gcollapse because it's not concerning itself with manipulating the data you have in memory, creating a separate data set or anything like that. It's just doing a printout, yeah? But if you need to save the result somehow, this can save the output into Mata, and then you can interact with it. And I do use that fairly often, because sometimes you have 3 groups, you want to look at summary statistics by group. Doing a collapse will be inefficient. You only have 3 groups, right? Doing collapses really should only happen if you have many groups, if you want to transform your data. Summary statistics by group, I think this is a very good alternative. Okay. Oh, I wanted to talk a little bit about this. I've coded this option to many gtools commands called replace, where if you've already generated a variable and you want to recycle it to save memory, to save time for whatever reason, basically every gtools command that generates a variable takes this replace option, and then it just recycles the variable. It doesn't regenerate anything, doesn't waste any additional memory. The only downside is that it doesn't check for type. So you should be sure that if you're recycling variables, it's the right type. So if you have a byte variable and you want to replace it with a mean, that's incorrect. You shouldn't do that. But if you already have a float or a double and you want to recycle it, you can use this replace option from any gtools commands and then save time, save space. So that's just like an FYI. Okay, and then the last thing is I want to talk a little bit about algorithms. If you make your loop extremely fast, extremely efficient, as fast as you can, that's going to be slower than a vector operation. That's what I said. Like if you want to compute a leave one out mean, and you loop through each observation and say compute the mean, but leave out this observation, that's going to be so slow. Again, everyone here I think knows the trick of doing the sum, subtracting their own observation, dividing by n-1. But there are many cases where it's not so obvious what to do. And why is it that your algorithm is so slow? And speaking of loops, if anyone here has ever done like a jackknife IB, I've seen code where they actually do loop through each individual row of data, and they say, do this, but leave out this observation. But there are cases where even that can be sped up if you know, like, if you can work through some matrix algebra. If you have if you're doing your regression, you have many fixed effects. Again, use available tools. RegHDFE for two-way fixed effects is going to be way faster than if you have your full set of dummies. And again, I think people here know this. So I'm giving hopefully examples that people here are familiar with so that you can see, yeah, really, if you make your algorithm better, your code will be faster, right? If you make your code faster and you don't make your algorithm better, your code may still be very slow. There's only so much that you can do in terms of speed sometimes. And then the last thing is that very often custom code is faster than general purpose code. So I think there are some like cases where you can probably code a faster reshape from wide to long than you reshape. And if you have that theory in your head and you know how to do that, you can spend a little bit of time and then get something much faster out of it. But again, trade-off, your time. If you're going to spend 10 hours making custom code, don't do that, right? If it's only going to take you a little bit to make custom code, sure, make the investment. It will probably be faster. Okay, so this is the example that I want to have for algorithms. And this is based on, again, something that happened to me last week. I had this professor come to me and say, hey, can you help me with this? Can you help me speed it up, right? So they were doing something like the second one. They were merging on like a double, and then they had the string variables. They had many string variables. They were merging on like 8-byte integers, actually. They had like 6 variables overall that they were using to merge. And I said, well, you have here variables. This variable is a date. You can have that be a 2-byte integer. This variable is an hour and a minute. You can have that be a 1-byte integer. This variable is an ID. You don't need to store it as a double. You can store it as a long. And then these 3 integers, you can concatenate them together. And suddenly you have a merge on like 4 variables, and all the variables are much more lightweight. And suddenly the merge was like 3 times faster. So being mindful of these types of things can be really important. I have another thing that I want to say here. Again, I was working with this health insurance data. The individual ID that I was given 21 characters long, very heavy. The first thing I did was that I made like an individual indicator from 1 to 80 million, mapped that to the ID. And then I worked with my integer indicator for the rest of my analysis. And I didn't want to look at that 21 character ID again, because it's so inefficient to work with such heavy string data, right? Integer, 4-byte integer data, extremely efficient, extremely fast, versus 21 bytes character data, very slow and much heavier, right? So just these types of things. And I don't think for many people, it would have been obvious to think, okay, like certainly for this professor, that's what will help you. If you have 6 variables, you can retype them, condense them, make them lighter, and the merge will go a lot faster. I'm sure you might think maybe the merge will be a little faster, but no, sometimes for a little bit of work in recasting data, you can get a big speed up. Okay, and then the last thing again, no program is the best at everything. Data is very easy to use. It can be slow sometimes. I certainly found it to be, but I think I've started data, so you don't have to. I've coded a lot of things in C. It's very hard to use C though. I wasn't a computer programmer. I kind of learned as I went. But I know it now, so whenever I need to do something that I really need to be performant, I go to C, but then I code an interface to Stata so that then I can use it more easily. Yeah? So depending on what you're doing, it might make sense to make this type of trade-off, but more often than not, sticking with what we know is perfectly reasonable. And before you get to see, by the way, MATA is Stata's embedded matrix language. It's very good. And if you're not using MATA, I think you should, and you already know Stata, you should spend a little bit of time learning at least some MATA basics. I found it to be extremely helpful. So starting from Stata 16, there's also frames, and you can have multiple data sets in memory, and that's also very useful. And lastly, there's a built-in interface to Python from Stata 16, and calling Python from Stata can be, again, useful for some types of tasks. One thing, by the way, that I've never done in Stata that I've always done in Python are Cartesian merges. So I've always outsourced that to Python, and because I found it to be pretty helpful. So these days for coding, by the way, I use Stata and Python. So there's a couple of tasks that I do outsource to Python, making plots, for example. I really like Python's matplotlib aesthetic, and it's very easy to manipulate it and things like this. And like I said, something like Cartesian merges, I usually use Python instead of Stata. But for other data management and analysis, I do use Stata because it's very easy. And at this point, I've coded enough tools so speed is not that big of a bottleneck for you. Okay. Now that's all I have, and I think I'm running out of time.
Thank you. Yes. Thank you. So we have some time for questions.
You can do the swap while not killing the swap from the mean. In the computer, deactivate the swap.
Oh, it's a bad idea to not have swap.
It was a provocation.
If you don't have swap in your computer, really bad things will happen. So either the operating system will start to kill programs until it has enough memory, because it needs memory to function, right? Or it will crash. And you don't want, if your operating system, if you think your program will take too long to run in swap, it will take even longer if your operating system is not working at all, right? Then nothing is working. So not having swap is a terrible idea. You should always have swap. It's like the operating system's like emergency space when it runs out of memory. It's just that when you're doing analysis, very often it's actually cheaper to kill your program and restart it with like a mindset towards saving memory than getting, just waiting until it finishes on swap. It's all I wanted to say about that.
Small. Because one thing is that if you do not have swap, you start asks for the RAM. And at some point, if the job is very large, it will say system refuses to provide more memory. Because one advantage is that it allocates that RAM. So including the operating system, no problem can take the RAM from the process. But it was
I think I only ever tried to not have swap once, and that was before I did any analysis. And I think the operating system I was trying to use yelled at me, and then I said no. And then I've never tried to run anything without swap. I think it would be a very bad idea. It sounds like maybe you've run into this issue.
Nice. It was a very nice presentation. Now I'm ready to go through my code to see if there are any different codes in my mind. So I have a question regarding what you just mentioned in the slide about using different languages for different purposes. So I'm talking from my own experience. I use it a lot for data manipulation, but I also use R for visualization for interactivity. And sometimes Python or a lot for web scraping. So it's a thing that we need to switch from one language to the other one. And one solution that we adopted within is to use notebook to call different kernels. Now you mentioned that in Stata we also have this new feature of Python integration. We can also call R within Stata. So I would like to know your view on like using Jupyter Notebook or use Stata to code these languages within Stata.
So the way that I code, I use a solution very similar to Make. It's not Make, but I use something that does the same thing. And I usually just call that and that automatically does my program. So I code files separately. I don't use like a notebook. I usually do everything like in the command line. And then once I'm done with the file, I integrate that into like a workflow and then it just runs. I know that in Jupyter, you can have multiple kernels. You have the Stata kernel and the Python kernel. And I think maybe you have an R kernel these days as well. And I knew somebody who liked that. My head just doesn't work like that. I think that I like these options because I think that people work differently. And I have found this workflow that I like where I don't mind switching from Stata for data management and analysis to Python for like scraping and visualization and things like that. Like I don't particularly mind it, but if you do and you want to use Python calls from inside of Stata or notebooks, that's great because again, those tools are available and they're pretty decent. So like the workflows in particular, I think are very idiosyncratic. And what you find that works for you, you should look for that. Somebody else might give you a suggestion, but for workflows in particular, if you're achieving the same goal, it doesn't matter if your workflow is different. Because I don't think there's an optimal workflow. There's just what works for you and what somebody else likes better. Again, you should try to make it automated. Like I don't use Make, but I use something that does the exact same thing. So if you want to try Make, you should try Make. And we talked about it yesterday. It's a great tool, but there's other solutions. It's not like you have to use Make. You have to use something that does what Make does, right? And it's not like you have to use what I do for switching between Stata and Python. You have to use something that allows you to do it more comfortably, whatever that is. Okay. So,
maybe just one thought. You've done a good job of sort of explaining how to sort of structure and develop when the big data is a potential performance stage. I noticed one thing that maybe is worthwhile pointing out. There is a difference between developing and debugging, and you get to sort of step one and it fails for some reason, etc. It's helpful to conceive of the last clean run through everything, the one that you launch at 8 o'clock at night before you go home, as potentially disabling some of those debugging features as well for speed. For instance, when you're talking about big data, if you have step 1, step 2, step 3, and you save your data set after each step, you are reaching out to disk, you're massively slowing down potentially your programming. And so to some extent, you want to also build in a feature. Okay, I'm done debugging. Now I just want to run through everything and I'm going to disable those saves as we do that.
Yeah, so I should say I have in many of my programs a switch called cache, where I will force the program to save data at checkpoints and then check for those checkpoints and load it back in. And when I do my clean run, I turn that switch off so that nothing is saved, nothing is loaded, it's just one run through. But you're right, that is important, and I did forget. So I do code my programs with this in mind, that I have this cached feature where it automatically picks up from the latest saved checkpoint, but I turned all of that off when I do a clean run because it is important to do one big run through to make sure that everything is working as is. And having checkpoints for that one final run through can be a hog, as is mentioned. Yeah.
We have an online question.
Yeah.
Okay. Let me read it to you. What about the, it's from Marcelo Santos. So it's, what about the matching process for different data sets? For those who work with panels a lot, It goes on and says data as country command, but it only works for very specific data sets. Is there a way to make it more efficient?
So what's the name of the command? Count?
Country, it must be a user written command, I guess.
Oh. I don't know it either.
I'm not aware.
I guess I'll make a note to have a look, watch the space.
Yes. Country with a K.
Yeah, I guess like I said, so for, I don't complain, I guess, about merging this database. No. Pre-sorting your data can help with that, especially if it's a panel, I guess. But like I mentioned, if you have to do something like a Cartesian join for some reason, so not one-to-one or many-to-one, but many-to-many, I try not to use data for that. But if you're doing many-to-one, yeah, I've never been too upset by status merges. I know that people do say they're very slow. But if I have many merges, I usually plan it for a time where I'm gonna have some downtime. So yeah, I've looked a little bit into making merge faster. It's very complicated, so I haven't gotten to it. But yeah, I'm sorry, I don't have a good answer. It's usually the thing I get asked about the most, and I don't have a good answer for it. This merging bit.
Okay, thank you. Do we have any more questions? No? Well, thank you, Mauricio. Next, we have Miguel Nelson.
Okay, hello everyone. If you want to follow the presentation, you can download it using this link. One more second.
So one thing, if you download the link, you will get access to an HTML file. And whenever we move the slides here, they move for you. But if you want to go back or forward on the slides, you can. Okay, so you are free to move on the slides on top of what we are doing. So it's a Dropbox link, download link.
Hello everyone. This is going to be a two-in-one presentation, so you have two presenters for the price of one. So let's start with introductions. I'll start by introducing Miguel, my colleague, Miguel Portela. He is a professor at the School of Economics and Management at the University of Minho. He's in the economics department, and also he's a consultant at Banco Portugal. I am also at the University of Minho, but a different department, management department. If you want to get more information about this, you can follow the links. So the presentation is about really big data. And so we'll try to deconstruct what we mean by data and what we mean by big, okay? So in the context of this presentation, you know that there are many different types of data. The one that we're going to concentrate is structured data, okay? So the tools that we're going to show you can handle different types of data, but the examples that we're going to present are all for structured data. And in particular, we are going to talk about rectangular data. Okay, so this is what we mean by data in the context of this presentation. We also know that big data is characterized by 3 V's, so volume, velocity, and variety. From the 3 components, we only deal with the first, volume. Okay, so this is the one that we are going to present solutions or possible solutions for the problem of dealing with large data or big data. So In this context, what do we mean by large data? Well, it's basically data that does not fit in memory, okay? And obviously, this is going to be relative. It depends on the size of memory that you have available to work with. So if you have a lot of resources, you can deal with a lot of data without struggling with it because you can fit that data in memory. Well, both of us are scholars here in Portugal. We are poor, we cannot throw money at problems, so we have to deal with the poor resources that we have. So the size of the data will try to convince you that you can do it efficiently, even if you don't have huge resources to do so. Okay, so we're going to present a data set that tries to illustrate this. We also know that you can scale this, so you can add more computational resources, both vertically, so getting a better computer, a more powerful computer, more RAM, more processors, or you can will deal with the problem scaling horizontally, so using a cluster of computers. We're going to show you tools that can do vertical scaling and horizontal scaling as well. Okay, so they can handle both. So what is the plan for the talk? We're going to present you three tools, three different open source tools for three types of or big categories of problems that we believe that can help, that those tools can help to solve. And finally, we're going to show or just give you a brief introduction to containers that can be helpful, particularly if you're doing horizontal scale. Okay, so if you want to do it without much trouble. So what are the tools that we are going to briefly present? The Apache Arrow project, DB, that is a database, and Apache Spark. And we're just going to give you a brief taste of it, okay? So any of these tools is quite complex and can be quite intricate how to use it efficiently, but we're going to give you a simple taste of how you can use each of them and show you that you can even combine the three tools together or go from one tool to the other without much computational effort. Okay, so this is also something that is quite important, mainly because the stage of development of these tools is not, they haven't arrived to a stable development. So there's still a lot of things going on, and we don't know which of the three are going to win in 1 or 2 years' time. Okay, so in 2 years' time, the tool that is best for the job today might not be the best in a couple of years. So it's a nice way. It's nice that we can change from one to the other without significant costs. So the first one is Apache Arrow, and Apache Arrow provides several functionalities. The one that we care about is the ability to deal with out-of-memory data. So we can deal with large data sets very straightforwardly. This is a product from Voltron Data. So this is a company that is in charge of the development. It is an open source tool. It is a brainchild of two of the very known people in both the Python community and also the R community. So I'm sure that most of you, if you know Python, you know Pandas. So the developer of Pandas is one of the co-founders of the project. And also, if you know R, you know the tidyverse, and Natalie Wicken is another co-founder of the project. So you have very good people behind the project, and it has been developed quite at a very speedy rate over the last few years. So what they have been providing is quite incredible in such short time period. The other one is DB. I don't know if you know this. This is a product, a open source tool created by academics at the Netherlands. So a research center at the Netherlands that are specialized for databases. So this is an extremely impressive product, especially because it was firstly released in 2019, and the ability of dealing with very large data sets is incredible. So this is something that you should be at least aware, even if you don't use it immediately. And finally, you have, oh, and by the way, that you can think about DuckDB as SQLite on asteroids. Okay, so the idea is the same, is to have a no server database. So you don't need a server, you don't need almost no configuration to use it, and it is a columnar format database that is very, very efficient dealing with data analytics. It was created exactly for that purpose. Okay, it is not a relational database. So you think about databases, you think about relational databases. This is not a relational database. This is a different beast altogether. Okay. And the result of that is that it can deal with very large data sets quite efficiently, okay, for the purpose of analytics. The last one, this is probably the most well-known, is Spark. So from the three, this is the oldest from the bunch. It is a multi-language engine for executing data engineering, data science, machine learning on a single machine or cluster. So from the three, this is the one that you can scale horizontally. So Arrow and DuckDB, you can scale vertically. This is the only one that you can scale horizontally. Okay, so this is very helpful if you have access to a cluster of computers. This is something that you can use very easily. So you have access to that. One of the interesting characteristics of these tools, particularly if you are using R, is that you can work with all of these tools using a single API, and that API is provided by BPLIM. So if you are an R user, you already probably know about this. So this means that we can write all our code using the same syntax as we would if the tables or the data tables were already in memory. And then we're going to have translations provided by these packages to use the tools that work on the same data set. Okay, so the advantage of this is that we can have only one source of data, and we can use different tools to access the same data. So we don't need to waste time importing the data from one tool to the other. Okay, so this is also a nice characteristic of these tools. And we're going to talk about three different types of problems, okay, that we encounter often. One, we start with a very large data set. We're going to do some filtering, some aggregation, and this is going to reduce the size of our data set, and then we're going to apply some models to it. So what we want is to do this filtering or aggregation as easily as possible, and then we can use whatever we are used to do or used to apply the models or to do the analysis that we want. Okay, so we just want to use these tools just as an intermediate step, and then we can load the data in memory and work as we are used to. Okay, so this is for a better name, we call it problems of type A. Okay, so we're going to have problems of type A, problems of type B. So it's not necessarily that we have a very large data set. Well, we can have a very large data set, but that data set can be subdivided in smaller groups, and we are only going to do the analysis at each smaller group. This is the case of time series. Okay, so in case of finance, you can have tens of thousands of financial assets, and you want to apply a model to each of those time series. And this is what we call a embarrassingly easy problem to parallelize. So we can parallelize this problem very, very easily. Okay, and we're going to show that there is some tools that can help us out in this step as well. And finally, we can have problems where we cannot reduce the size of our data. The data does not fit into memory, and we want to apply an analytical model to our data. So how we can do that? Well, from the three tools that we're presenting, Spark is the only one that can help you out. Okay, so There are other alternatives, but this is the only from the set of three that we're presenting that can help you out. So what are the language that we're going to use? Is R. If you are using Python, you can also have interfaces to all of these tools in Python. If you use Julia, you can also use it with any other without any problem. If you are using Stata, well, you probably can use it through Python. Okay, now, so I think that's the only way that you can do it. So what is the data that we are going to use to illustrate the advantages of using these tools? We're going to use intraday data for 251 days, so basically a year. For the B3 financial exchange, so the financial exchange at São Paulo, Brazil. And this is from July 22, 2021 to July 22, 2022. Okay, so a year of data. Is this big data? Well, not necessarily, because it's not enough doing anything. Okay, so it's just a year. If you want to do any academic work on this, you are not going to be able to. You probably need at least 10 times that. Okay. Is this troublesome to work with? Well, it is a little bit, because we have the data is originally distributed as compressed text files, so between 49 and 82 megabytes. And that corresponds to 2.7 billion observations. Okay, and we are only talking about trades. Sometimes we have bids and asks, so we also have quotes, and this is orders of magnitude larger than that. Okay, so for the same time period, we would have 10 times or even more observation than this. Okay, so is this big? Well, for the context of what we are presenting, it is big because we cannot build it in our laptops. Okay, so we cannot work with that. We cannot load the data directly in our laptops. We can follow the advice of Mauricio, so we can do it in chunks, but this is exactly what these tools are going to do for us. Okay, so we don't need to program that. This is going to be done by the tools themselves, and it's going to be transparent for us. So we're going to use the same code that we would for data that is in memory to work with data that is out of it. Okay. And we also have some metadata on the financial instruments that this is quite small, just 14.5 million observations. Okay. So we're going to present some times. Keep in mind that these times are merely for comparison between the tools. Okay. We can do it better. It can be worse depending on the software, the hardware that you have. So don't pay too much attention to this. This is just to compare the tools within the same hardware. Okay, so let's start with the first type of problems. We're going to do some exploratory data analysis. And this is the type of exercise that these tools can be quite helpful. So we start by loading libraries. We have a directory structure. So basically we have our files, and all the files that we have are not text files any longer. We are using Parquet files. So if you don't know the format, Parquet format, it's a binary columnar format, very efficient, both in terms of compression and also in terms of input output. And this is almost a standard for big data tools. So most big data tools are going to be able to ingest Parquet files. And this is what allows us to use the same data using these three different tools. Okay, so let's start by doing starting the connections. This is the part that is going to be different from using Arrow, DuckDB, or Spark. Okay. So this is the part that is going to be slightly different if you're using the one of the three tools. But that's it. We just need, in the case of Arrow, we just need to open a data set. In the case of DuckDB, we need to start the process, the DuckDB process, and then just register that set of files as a table. We're not reading the data, we're just registering, it's just creating a pointer to those files. And in Spark is similar. We start a server. In this case, we are starting a server, okay, a Spark server locally. if we have one that is available in a cluster, we just connect to it, okay? And then we just need to read the Parquet files. And again, this is just creating a register where those files are, and that's what we're going to use later on. Okay, so can we do simple things? Well, what we do when we start with data, we count the data, at least to know how many observations we have. So if we're doing it in arrow, it's going to take 119 seconds. Okay, not bad, not very impressive, but it is doable. If we do it in DuckDB, we can have this exactly the same result in 0.16 of a second. Okay.
Sorry to interrupt. These are times in our Mac M1 computer. So none of this is done in a server. Okay, just it's 2.7 billion observations. These are times on that laptop.
So in Spark, we get 4.3, okay, seconds. And notice one of the things, what are we doing? We start, this is the object that contains the reference to the tables that we've created, okay, initially when we configure the tools. And then we do a simple count. So this is what we would do it if we were working with dplyr. And the only difference is that at the end, we want to say that I want to collect that result into R, because none of this is being done in R directly. Basically, what R is doing is calling these tools to execute those commands. And then we want to collect the result into our memory later on. So that's what we are doing here. Notice that the commands itself remain exactly the same. The only thing that changes is the tables that we are using. So basically the registrations that we've done previously that are going to use different tools. Okay, but the commands are exactly the same. So this means that if I can start an analysis in arrow, go to DuckDB, and then add Spark later on, and it doesn't mean that I need to change the way that I code my code to do the analysis, okay? So if I want to count the number of instruments, again, I will first start with the data set, then I will obtain the distinct values of the tickers, so the instruments are identified by tickers, and then I'll do a count, okay? Again, in arrow, this takes 15.2 seconds, in DuckDB 7.7 seconds, in a laptop, again, okay? So, and Spark, we do it in 44 seconds. So it's going to be different. The best tool for the task is going to be different, or it's going to depend on the task that we're doing, okay? So, but notice that I don't need to change anything about my code to go from one tool to the other. If I want to count the number of trades per instrument, I'm not going to show the result, but this is simply count the number of trades that we have for each of those instruments in the data set. I can get a result in arrow in 16 seconds, in DuckDB in about 9 seconds, and in Spark in 33 seconds. Okay, so again, quite doable what we're doing. The data has two dates. We have report date and the trade date, and we wanted to know if the dates were different, or there were instances where the two dates were different. And we have, okay? So there are a few instances that we should be careful dealing with the information that is there, because the report date and the traded date is not exactly the same. And sometimes that happens because some trades are not recorded on the date that they occur. They are recorded on the day after or a few days after, okay? So there are some problems, or this might be some examples of incorrect observations that we have in there. So this is something that we can do in DuckDB in just 1.6 seconds. Okay, so this means what? That I can deal with a very large data set with a very sparse hardware resources in a way that invites playing with the data. So this is the thing, at least we're not young anymore. We get old, we get cranky, we don't have the willingness to wait a long time to get a result. And if we start to wait a long time to get a simple result for an analysis like this, this means that we're not going to explore the data as much as we would otherwise. Okay, so this invites us to play with the data. So if I just want to get a plot of the evolution of number of trades per day, I can get quite easily using the syntax that everyone in R, most people that use R is familiar with in just 1.7 seconds. Okay, so this is from nothing to the plot in less than 2 seconds. So again, it invites us to explore the data to see if there are any problems and to at least be a little bit more happy with the analysis that we're going to perform. So we can also do some checks. We always need to do plenty of checks to see how reliable the data is. And one of the ones that we need to perform is to see if we have prices that are less than 0, okay? So this is not necessarily in the case of finance, as you might know, this is not necessarily an error, okay? So if it was common stocks, that would be necessarily problematic, but it is always nice to check if we have negative prices for those trades, and we do, okay? Again, very easy. We're doing a filtering of all observations that are less than 0, and then a simple count, and we can do that in less than 4 seconds, okay? We can also select common stocks, and to do so, we're going to do a semi-join with the other data set that we have, that is the metadata about those instruments, and a join of those 2.6 billion observations with 14-point-something million observations is performed in about, we don't have the time here, but if
740.
pardon?
740.
It is about 12 minutes, isn't it? Yeah, about 12 minutes.
It's a merge between 2.7 billion and 10 billion.
It's not really a merge, it's a semi-join, so it's not, we're not merging the data, we're filtering the data, okay? But again, this is not something that is usually very fast in the case of, particularly in the case of large data sets, and this is something that we can do. It takes a little bit more than the previous examples, but it's doable. And then we're going to show you an example of calculating daily realized variance. So basically, what is daily realized variance? We calculate returns for sub-frequencies within a day. It's usually 5-day returns that we use, and then we simply sum the squares of those 5-minute returns. Okay, so then we do it for all the instruments that we are using. Okay, so we're going to end up with what? A realized volatility measure per instrument per day. Okay, so this is what we are going to use. This is the code. It is a little bit too long. The sequence of, I'm not going to describe it. I describe it what it does. It's simply doing some filtering. I'm just making sure that I'm selecting the trades that, first of all, correspond to common stocks. Okay. Secondly, that fulfill some requirements in terms of the markets that they occur. I'm also removing observations where the trade date is less than the report date. I am making sure that I'm selecting the trade that occurs closest to the 5-minute mark, okay, for each stock for all the days, okay? And then I'm going to calculate what? I'm going to calculate by stock and by day. I'm going to calculate the return, square it, and the sum per day, okay? And all of this takes 12 minutes, okay? It is more computationally expensive, it takes a little bit longer, but it's something that we can live with, okay? And now we have what? We have now a measure that we can use as something that I can load into memory and work with the models that I want to do. For instance, we can do a R model on this, okay? So I'm sure that this is not something that most of you are familiar, but this is a simple regression. This is called the heterogeneous autoregressive model of realized volatility. It was first introduced by Course in 2009, and we simply do a regression on the current volatility, realized volatility, on the previous realized volatility, the weekly realized volatility, and the monthly average realized volatility. Okay, so it's a simple regression. But this is something that we're going to need to apply for all of those instruments. Okay, this is a regression. This is very fast. Okay, this is not a good example of a computational hard or expensive calculation, but it just gives you a taste. Okay, it could have been what? It could have been a Gauss model that is much more computational intensive process. Okay, it could have been, and this is what we would do it in practice, to do it as a rolling window estimation. Okay, and then calculate how well the model performs in terms of forecasting future volatility. Those would be more expensive, but we will need more data. Okay, funnily enough, we don't have enough data to do that. Okay, so this is not enough to perform those models, but we can show you how we can do this. First of all, parallelizing and not parallelizing the process. And for doing so, we're not going to use any of those tools. We're just using straight R. And using straight R, we can do the parallelization very, very easily. Okay, so this is the code that allows us to calculate the regression for each of those instruments. And in R, it's extremely fast. And it's going to be extremely fast in any language. Okay, and then we have with parallelization, this is a good example, okay? Doesn't mean that if you can parallelize, you should parallelize. It takes longer, okay? Why? Because this is such a computational, less intensive problem that parallelizing the problem is just creating overheads, okay? But the only thing that matters is that if we want to parallelize, we just need to use a simple command at the beginning. Okay, we can scale in this case vertically. If we wanted to scale horizontally, we use the same command with a different configuration, and then we can just use the, instead of mapping the function, we use a feature map, and we can do it very, very easily. Okay, so in terms of coding, this is something that can be done quite easily.
So let me just go back to just wrap up what Nelson discussed over the last minutes. This is the following. You have data in a very efficient format, Parquet. You have dplyr, the commands that you know how to type, and will be the same commands irrespective of the tool that is doing the job. So the code stays exactly the same. The only thing is that in the beginning, you specify arrow, DB, or sparklyr, and everything else is the same. What changes is the time of computation. So you can go from 44 seconds to 0.2 seconds, from several minutes to some seconds. So this is to wrap up the idea. So Nelson talked about the parallelization, the use of these tools, and now I'm going to move. I'm going to talk about using the full data set and running regression analysis. So one note, most of the things that Nelson showed is explanatory data analysis, aggregation, average variance, and so on. Nelson already showed some regressions. One of the things that the two of the tools, namely Arrow and DuckDB, for example, they do not perform regression analysis. So now I'm going to use to focus on Spark to run that feature. So I'm going to use the data by BPLIM and Couture. So Yannick is going to talk after me. So I'm going to take the data. So the data has something like 137 million lines, is a 30 gigabytes CSV. And I just want to say that in Parquet, it's just 3 gigabytes. So typically Parquet can be the same information, 10% of the CSV files that we are getting. The data is the whole marker's disclosure. I'm not going to pay attention to the economic model or to the parameters. I'm just going to show how performance changes according to to some of the tools. This is just out of curiosity, the descriptive statistics, and I'm going to use in Spark a specific tool, which is the machine learning library. So the ML lib. Okay, so you can run neural networks, random forests, but at the same time, it has pre-programmed tools for estimation linear models, and as well as duration models, probability logic, and some other models. So to estimate such model, and yesterday we had an example. Basically, what changes is if you have knowledge on R, is that if I'm using the typical linear model, I would start by typing LM, and here I'm starting that command. So at the end of the day, the change of the code is not that much. What you need to know is, if you go back to the previous diagram that I've shown, so in this case, the computation is not done through the typical data frame or data table in R, I'm going through Spark. And that's what increases the speed of the computation. And here I'm going to talk about two things. So far, everything that you have seen all the times, they were computed in my laptop. It's an M1 laptop, 16 gigabytes of RAM. So, and we are dealing with 2.7 billion observations. If I run this analysis, so a very simple regression, 138 million observations, my laptop took 12 minutes, okay? So now I'm going to ask, okay, let me move to a real server, what will happen? So I went from my laptop to a server that has 32 processors and 512 gigabytes of RAM. So, okay, so I'm vertically improving the capacity of my machine. I just cut the time by half. So you see that several of these techniques, so far we were improving the times by changing the solution, the Spark, Arrow, or DuckDB. Now we say, okay, on top of this, let's move up the ladder, improve the machine. And in this case, it's basically the time that you are getting. We are not exploring the going through a cluster, so the horizontal expansion in the bank, we have a cluster of 14 servers, all of them is 512 gigabytes of RAM and 32 processors. So in the future, I'm going to try the same computation then using the full capability that we have. So now the containers. The big question is probably at the end of the presentation, you are going to ask how I can put this on my computer. Okay, you want to try it, how do I play with this? So one solution is install R, install all the packages that we have, and eventually you might run into some trouble because your operating system you need to install additional packages and so on. And this is where the containers come in. Because if you want to try within 15 minutes the entire solution that we have designed, you just need a container. We give you the container, we have a container for the solution. And what is a container? You can think of a container as a virtual machine, okay? So I have my laptop, and this is a big file that contains everything, the operating system, the graphical interface, and also the code that we have been using. For you, in this particular case, because the container occupies 1.4 gigabytes. So compare with your laptop, you have gigabytes and gigabytes of your operating system. Here, the entire solution is 1.4 gigabytes. So at the end of the day, I just give you a file or I point you to a link, and you can start basically running exactly the same information. So a key feature of containers, and last, the American Economic Association is using the solution, which is the containers are, let's say, the state of the art of the tools for reproducibility. So the author, at the end of the day, if the author has a container with the entire analysis, basically, I will be able to reproduce the analysis as long as I have access to the same original data. You probably didn't notice, but I did say that the data is inside the container. So Imagine that I have my laptop with the data is in the laptop, I have the container. I move, and that's what I have done. I went from the laptop to the big server. I have a replica of the data, same container, same results. It takes me a couple of minutes from moving the solution from one side to the other. So I will give some time for questions.
Thank you, Miguel. Questions? I guess I have a question. I didn't see a link to go and download the container from. Is that such a thing?
There is. So we are going to provide it later in the presentation. Later with the presentation. So as you have seen the presentation, I realized that some of you were not able to download the presentation. You cannot be within a VPN. So if you are at the bank, you should not be using a VPN. It doesn't work. So if there is a firewall, you won't be able to download. The presentation itself was a contribution because we are Nelson designed an Quarto PowerPoint that allows you exactly to be following the presentation. So later on, you have the presentation. We will update the presentation with a link to the content. By the way, the container, although the container is a 1.4 gigabytes with everything, I just need to give you the script that builds the container, which is a 5 or 6 kbytes script, and it replicates exactly my container. So at the end of the day, I don't need to give you the container, just the script.
A quick question, maybe a bit naive, so I apologize in advance for that. But using the tools that you presented at the beginning, so from what I understood, we don't have to have the data in memory. So where is the data stored and how it relates to GDPR compliance?
It is in files on your computer or wherever it can be on S3 containers, it can show in the cloud. It can be on your local file system, it can be on a data lake, so it really depends on the context. But it's just files that you can access like any other file, okay? So if you're reading CSVs, this is just like the same. Okay, and by the way, both RLDB and Sparkly R also work with CSVs directly, but it's not as efficient, okay? So you don't need to use Sparkly files to use these tools, but it's not going to be as efficient.
So it has nothing to do with where the storage, data storage is just, okay.
So you can have the files on your computer solution. Imagine that you have the protocol within Attribute Swap. You can locate this in your computer. But for example, there is a famous paper by Bonomic and co-authors at Economics where they provide the container. They are using confidential data from Sweden. And the only thing you need, so the data is not in your hard drive, the data is not in the container. The only thing is that you need to have a login and a password for the Swedish computer, because the container starts the connection and you just need to password and login and that's it. So the container will know where to look for the data. Okay. So the files can be wherever you want. Yeah.
And you've been talking about very nicely about structured data. What about unstructured data, like text data? Because I've been using a lot of Parquet as well, and it works really well. As you said, it's always like 10% of the size of the original file. But I don't know if it exists like any other sort of framework like DB for text data and so on. What's your view on this?
Eventually, you're going to transform that data into some numbers, correct? So there will be some transformation, and that transformation, I would say it's close to problems of type B. You have a very large data set, but you can subdivide that into chunks, the documents, and then you are going to perform some action on those documents. So probably the hardest part is how to parallelize that to make it efficient. And for that, there are many solutions that you can use. And Spark, for instance, have models, machine learning models that are specific for text. So that is straightforward in that case. But since it's not a problem of fitting the text, the documents into memory, each of them is just how fast you can parallelize the process over many processors. That there you have very many solutions. Within R, Future is a good example.
Just one note. So this is a great paper, 2022 paper. And the one thing that I did not explore, I just mentioned one example with OLS using the MLib library, but they estimate panel data models and time series models over SPARC, which are not available in MLib. Okay, so explore the data for econometrics at a scale. More questions?
We have some online.
Yes. I have some doubts about the process. So we can have the data wherever we want. So we can go there and pick up the data. And this works online. You must have an internet connection or no? So it runs in your computer?
It depends. If the data is on a S3 bucket, for instance, or a data lake that you access through a network, then you have a network connection. If the data is local, you don't have a network connection. There is no need for that.
These kind of programs are not online?
No.
You don't run online and
No,
after you receive in your computer?
Locally on your own computer or on a cluster of computers.
So
you have to download the program?
yes. You have to, so the tools that you need here is you need R, and then within R, and you will use probably the graphical interface is RStudio. So one thing that you have to install R, and then you will need to install these packages. Everything
They are
on your-
package of R.
They are
Yeah.
packages of R, yes.
Yes, there are
In
a
the-
set of packages.
And the only thing that you are required to install additionally is the Spark server. Okay, so the Spark server is run.
But you said that we need a registration.
That's the.
No,
So imagine that I'm working here. So in a typical situation, how have I worked on my computer?
no, I think that the registration comes from the example of the
Yeah.
Swedish data.
Yeah.
So
So
it's-
the software,
Oh, the software don't need a registration?
no, it's open source. Everything is for free. It's open source.
This is libraries.
Yes, these are libraries.
Yeah,
Yeah.
yeah.
So for example, at the bank, if you have Pythagoras, in Pythagoras, the data is already in the servers, in the data lake. And you can either have it on your laptop and it communicates with the data, or again, the container is the perfect solution because everything is installed and the data is outside of the container.
I have here another question.
Yeah.
Do you have a way to transform CSV to Parquet?
Yeah.
There are ways?
And
It's,
very efficient as well.
Very efficient.
Arrow provides those. Arrow nowadays probably it's in R is the fastest way to read CSV files. And you can read those CSV files and convert it into Parquet by chunk by chunk. Okay, so this is transparent. So you don't need to load the data into memory and then convert it into Parquet. This is done on the fly. Okay.
So just a fast note. Here, I'm still running out of memory. Out of the memory, the data is on the hard drive. Okay, so in Pythagoras in the server, I have enough RAM to upload the data to the RAM. So that would improve the time. Okay, so far, the files were all the time in the hard drive. The RAM is not being used for this, or just a little. That's why we can use these data sets.
We still have a couple of online questions. Let me move on to these online questions. So the first question from Sebastian Buhai, actually, I think Miguel already answered. It has to do with the magic of this presentation. How come you are changing these things? And Miguel already mentioned it was
It's called multiplex.
but is that true part or not?
It is true part.
It is true part. Yeah. And so I'm going to skip that. And so the second question is, since both Miguel and Nelson appear to have done this, how much disk space does it take to install each for all of Arrow, DuckDB, and Spark, both fully functional. And if you, okay,
It's fine.
on a typical late generation laptop.
The content, everything, it takes 1.4 gigabytes. The operating system, the graphical interface, and the packages.
For the three libraries, I mean, with Arrow, DuckDB, and
A
Spark.
working container occupies 1.4 gigabytes.
Wow. So, and I guess that relates with the second question by Bernardo Costa. Any tips on how to install Spark? It seems difficult to install, especially in a cluster. Also, do you have experience with Dask? If so, how long will it compare to Spark, Python implementation? Will be the last question.
Okay, it can be tricky to install Spark on a cluster. We are not engineers, so I'm sure that they would provide better ways, but circular generalization and a orchestration tool that can be significantly, well, the complexity can be decreased. Okay, so for instance, if you use Kubernetes, that can be a solution to that.
Just a note, Nelson has a PhD in finance, I have in economics, so we are far from engineers.
Well, thank you very much. Okay, next, Yannick Coutura. This is an online presentation. Unfortunately, we had to change plans at the last minute, but luckily enough, Yannick can still be with us, although online.
Can you hear me now? I think now you can hear me. No? Yes?
Yeah, you can go ahead and start.
Yeah, I'm trying. Can you guys hear me?
Yes.
Ah, okay, perfect. Sorry about that. Okay, then here we go. Yes, first of all, thank you so much for having me. I consider myself very privileged to address this audience today. So what I'll talk about today is a bit how we can use distributed computing like Spark to help us with really data-intensive workloads. And the more funny title to that presentation is, why is my computer so slow? Let me go. So in terms of the target audience, I had originally designed this presentation, or rather an extended version of this, for an internal ECB talk, because after working there for a year or two, I kind of realized that, you know, in my humble opinion, we have really excellent economists, excellent econometricians and statisticians. But what we can do a bit better is the whole data handling bit, right? So what I've observed a lot of people struggling with is, how can I use all these new large granular data sets that we have available now to really make sense of them? And it typically wasn't so much the regression bit that people struggled with, but really just the reshaping, remerging, and matching of these data sets, right? So that's really my target audience here, people with a very limited background in computer science, and people to whom maybe, you know, the whole coding and writing codes and the data engineering bit is really a necessary evil, but you want to do the economics, but you have to do this, okay? So I hope this presentation can help you get there. I think there is one dead giveaway whether you might stand to benefit from this, and it's summarized here in this little quote, right? So say you have a new project and your first instinct is to download all the data from the sources that you have. Maybe you have an Oracle data warehouse, or maybe you have a huge network drive where you have a lot of files stored, or you do a lot of web scraping, or whatever the case may be. You put that all on your own laptop, and then you start your Stata, MATLAB, or Python, whatever may be the case. So if this is you, maybe you stand to benefit a bit from this talk today. So the first thing that I want to accomplish is to understand why your computer gets slow when working with big data. And here I'll go a little bit more basic than the previous presentations. But again, if you have a limited background, I think this is a good level to have this conversation at. Okay. Then I want to show you how a distributed system like Hadoop and Spark works under the hood. And then I can hopefully convince you that those will be useful to speed up your own data handling and analysis. So yes, again, nice meeting you. Regarding my background, I'm an economist by training, but then somewhat transferred towards data engineering and software engineering, and when I started, well, I finished my PhD and started as a PhD trainee at the ECB, that really was a happy coincidence of once, as the economists would put it, because we just started to become available a lot of very granular data sets. At the time, AnaCredit was very popular, which is basically a credit register for all of Europe. So when I started working with it, that was 300 gigabytes of data already in Parquet format, so stored very efficiently. And then you can imagine, to really make sense of this, maybe you want to merge it with bank balance sheet data and maybe company borrower balance sheet data as well. And then maybe for the banks, you also want the security holdings of similar companies or derivative positions or whatever the case may be. So quite quickly, if you have this kind of information available, and in the end, it needs to go in some Excel plot, you need to have sort of this middleman with a data engineering skill set, right? And this seemed to me to be the bit where many people in central banking struggle with a little bit. And this is why I try to have this presentation help you. Okay, so the paper was shown already. In this paper, what I did for my PhD was review a bit how you can use econometric models. But honestly, after 2 years in central banking, I think I missed the target a bit in that paper, because I was aiming for this thing, right? The fancy econometrics, machine learning, artificial intelligence bit, because that's cool and everybody wants to have that on their website. But is really this bit that's killing us, right? At least in my experience, this is the big bottleneck, why projects fail, why stuff just doesn't go anywhere, because people struggle to really get the data in the right format to do the analysis. So let me see if I can help a bit with that. So when you work with big data or data in general, I would raise you have 4 options. You have your own laptop. Maybe you have like a remote desktop, Citrix. Maybe you have some kind of a data warehouse available at your institution. And maybe you have Hadoop or Spark. And for today, clearly, I want to talk about the latter, though I will relate to the other ones quite a bit. So in case you've never seen Spark before, if you at your institution have a Hadoop Spark cluster available, like we do at the ECB, the first thing that I always show my students, just so they have a connecting point to it, is this thing here, which is called the Hadoop User Experience, UI. And this is opened in the browser, right? I just screenshotted this. And this looks maybe suspiciously familiar if you're used to any kind of SQL database data warehouse, right? Something like tables over here. Here I have the variables in the table. Here I can write something that really resembles SQL. And then I can click execute and I get the result here. So that's actually quite nice. But of course, you can also have the data being sent to your computer, right? So this is instance data, but of course that works for any software that you like to work with. You can just pass a SQL query, like here, select star from my database.mytable, and this will simply download all the data to your computer, and then you can work with it, right? From a data warehouse, or like here, from a Spark Hadoop cluster. And basically, what I want to convince you today is that doing this select star from table is a really, really bad idea. Okay, and we want to look at that in just a second. But first, let's quickly have a look into what's a Hadoop cluster, right? So there are many providers for this, both on premise and in the cloud. As an example, there is CDH, Cloudera Distributed Hadoop, which is an on-premise Hadoop cluster installed by Cloudera. It's running the Cloudera Distributed Hadoop software. Okay, that doesn't really help a lot. So let's break that down. So on-premise just means you physically own the hardware. You can do this in the cloud as well. What's a Hadoop cluster? For now, let's just say it's a set of connected servers. A server is just a computer, which are running the Hadoop distributed file system. What's Cloudera? Well, that's a company that makes a lot of money by selling these big data analytics solutions. And what is that they really do? Basically, they configure the Hadoop ecosystem. So as we have heard in the previous presentation, all of this is open source, right? So believe it or not, but you can go to the Apache Foundation's website later. You can download the entire Hadoop software, and then you take your laptop and your spouse's laptop. You're gonna wipe them clean, connect them together, and then you can try to install your own Hadoop Spark environment. But chances are you're gonna fail quite miserably, and that's okay. I would fail quite miserably as well. It's quite difficult to get this right. So usually we have a company that does it for us, like Amazon or Databricks, or whatever your favorite provider is. Now let's get to the juicy bit. What's the Hadoop cluster? We'll return to this picture later, but for now, let's just say it's a set of connected computers, right? That's these guys down here, the data nodes. And there's a master node that sort of keeps track of what's going where. And then there's a client that you can talk to from your local laptop and ask to read or write data. So the important thing to see is it's a system that scales horizontally, right? It's not that you take one computer and you make it ever more powerful, it's that you have many, many computers connected. Okay, but what is this thing solving? To understand that, we have to have a little primer on computer architecture. And if you're a computer engineer, if there's anyone in the audience, some of what I say might make you want to peel off your fingernails. This is a very high level overview just to help understand what's going on here when your computer gets slow. So believe it or not, whenever your computer gets slow, is usually for one of three reasons. Either your central processing unit gets busy, your random access memory is getting filled up, or you do some kind of input-output operation, which is to say that you're reading data from your hard drive or from some kind of network drive from the internet, and that takes a lot of time, right? Now, if you don't believe me, next time your computer is slow, you can press Control-Alt-Delete, and then this little guy here pops up, the task manager, and you can see the 4 categories here, yeah? So one of them will likely be close to 99 or even 100%. Now let's understand a bit how those work together so that then we're able to sort of diagnose our own programs when they run into those problems, okay? So we have these 4 components, and let's say we have 2 numbers that are either stored on the hard drive or somewhere on the network or the internet, and we want to compute the sum. So that's easy enough, but how does it work really in the computer? So the first thing that you have to do is you have to read it into memory. And then once you have the data into memory, your central processing unit can access it and compute the result. So let's try to understand the different bottlenecks that can happen in such a situation. So first, what about the input-output bit? When you read from your hard drive, nowadays, it's actually quite fast. Back in the day when we had these magnetic drives, so really there was some physical element that was spinning and that was quite slow. Now this is a bit less of a problem. But on the other hand, of course, in particular, if you work in central banking, you will know you're not supposed to use your computer's hard drive, right? Your computer could get stolen, it could you could lose it, or it could break, and then you might lose months of work. So you're not really supposed to do that. Now, what about network drive? This can be really painfully slow, and I'm sure all of us, most of us, have experienced that. And in particular, if you're working remotely, right? Have you noticed? If the data from your corporate data store of whatever nature that might be have to travel through the public internet to get to your computer's memory, that can be quite a pain. Okay, so that's the first bit. Let's understand the second bit, the memory. Clearly, the 2 numbers are going to fit in, yeah. But as we have seen in earlier presentations, this will become one of the main bottlenecks as you work with big data, right? So what does big data mean in this context? Yeah, it depends a bit on your hardware and on the problem that you're tackling. So I have 32 gigabytes of memory in my ThinkPad. I need a couple of gigabytes just to manage Windows and my Chrome browser. So maybe I'm left with roughly 20 gigabytes, something in the ballpark. Maybe you have a strong computer, maybe a weaker one. But as soon as the data you're going to work with gets considerably bigger than 20 gigabytes after reading it in, that can really be a problem. Now, the computer science nerds would call this a space complexity problem, right? There's just not enough space for us to hold all the data in memory that the CPU might need at a given point in time, and then we might need to spill it to disk, and we don't want to do that. Then the central processing unit, once we have the data, well, some tasks are computationally really expensive, in particular if we cannot parallelize the operation, right? Okay, so let's recap. I think this bit here, most people have experienced so far. This can sometimes be a bit confusing if you're not like super familiar with computers and all. So let me just give you an example. That's very stylized. You're not going to run into this in reality, but just bear with me here, okay? Imagine you have a matrix of 100,000 by 100,000, and it's just zeros in there, okay? Now imagine you add 1 to each cell. What's the result? That's quite easy, right? It's just the same matrix, but there's now 1 everywhere. Okay, easy enough. I can do this. So now let's Python have it done. First, I'm importing NumPy, which is a linear algebra library. And then I'm initializing this variable here called zeros and set it to, well, a matrix zeros with these dimensions. And I run this, and immediately when I run it, I get this error, okay? And it's worth trying to understand the error. So what Python is telling me here is you have a memory error. Okay, so something with my memory. Python is unable to allocate 74.5 gigabyte for an array with this shape and this data type. So what does this mean? It means that just initializing this array, right, just populating this array into my computer's memory already blew up my memory, and therefore Python is refusing to do it. And it's important to see here that it's not the +1, right, that's killing me. It's just to set this up, right? You can imagine if you read in a lot of data, then you might get exactly that same kind of problem. Okay, so that was space complexity. Now let's look at time complexity. There's a famous sequence called the Fibonacci sequence. Those of you who don't know it, you start with 0 and 1, and then you just compute the sum of the previous two. Yeah, so 0 and 1 is 1, 1 and 1 is 2, 1 and 2 is 3, and so on. There's different implementations if you were to put this in code to get to the nth Fibonacci number. And let's try to think about one of those and then try to understand the space complexity and the time complexity. So the way that is intuitive for me to code this would be something like this. So I know start with 0 and 1. So those cases are trivial. So then to get to the first real number, let's say I take those two, compute their sum. For the next ones, okay, yeah, I would take the sum of these two, and then the sum of these two, and then the sum of these two. So what about the space complexity here? Well, at whatever step I'm at, I really only need two numbers, right? I don't need those zeros and ones up here once I'm down here. So this is something that a computer scientist would call its constant space complexity, right? Because no matter how far I go out in the Fibonacci sequence, right, it's always just two numbers that I need to remember in order to compute the next. Okay, so that's good. What about time complexity? Well, if you think about it, the way you do the sum, you really have to do n computations to get to the nth number, right? There really seems to be no good way to break this down, right? Like I couldn't tell you, look, I'm gonna split the work. You're gonna compute the second 5 here. I'm gonna compute the first 5. Because for you to start, you need to know my result. But if you need to wait for me, then I might as well do it myself, right? So this is something that we can't really break down very well. We can't really parallelize it. Okay, so since it needs n steps, this we would call linear time complexity. Okay, so how can distributed computing help you? Well, first and foremost, I would say if you have a space complexity problem, that's really the big one. If the data is considerably bigger than what you have available in your retail grade computer's memory, then this can really help you to be able to handle the data. Rule of thumb, I would say anything above 25 to 50 gigabytes or more, you could be considered big data. And by this 25 to 50 gigabyte, I mean something that's already stored efficiently, right? Secondly, you have a time complexity problem that can be parallelized. Yeah, so any kind of computation that can be split up into individual parts and can be evaluated in parallel. So we have seen one where you cannot do that. But for example, if you think about this one, the sum of the first 10 numbers, I could do the first 10, you could do the second 10, and then we can sum that up. Okay. And thirdly, input output. If you lose a lot of time reading in large data sets from the network drive to your laptop, then a distributed computing solution is likely able to help you as well, because the idea would be instead of reading all that data, do you take the computation to the data rather than taking the data to the computation. Okay, some caveats. Well, first and foremost, you must have access to Hadoop Spark cluster, right? And that might not be something that you can influence easily. If you really have to have one in your institution on premise, that can be quite expensive. I think a big game changer here is the public clouds. So for the paper that I originally displayed, I think I paid less than 100 euros for the entire paper, and I was spinning up an Elastic MapReduce and Amazon Web Services quite some time to do these calculations. So, you know, there might be a lot of change coming, hopefully also to the institutions in this regard soon. Next, you must be able to express your data manipulation in either the Hive or Impala SQL dialects or in Spark directly. So many, but not all features I would say implemented there. Obviously, regressions is something you wouldn't want to do in SQL. Spark, on the other hand, offers quite a wide range of those. At the same time, I have to admit that if you're looking for something very fancy, maybe like the Rec HDFE multi-wave fixed effects with two-way standard error clustering, Maybe not all of it, but maybe soon. And then the third point that we'll raise to you is that even if this is not met here, I would argue that you can get quite some benefits from interacting through any programming language that you usually like to work with your distributed system. Yeah, okay. So let's take an example that really shows the benefits of doing that. Yeah. So let's say you have a huge data set and you just want to compute the average of all numbers. So it's actually a bit simple, a bit close to what we've seen in the last presentation. And now you can see what's happening under the hood here. Okay. So this is the old bad way. So this you should not do. So what you should not do is either really reading in a big file from your network drive, right? Or do the select star from some SQL table that you have available to you. What were the problems here? Okay, so first of all, it takes a lot of time to download this data to your computer, right? Secondly, if this is really a big file, it's not gonna fit into your memory. And thirdly, whatever computation you then do in the end, like computing the mean here, could take a lot of time depending on what it is that you do, right? So what's the new good way? The new good way is doing something like this, either in this Spark Hadoop viewer on Huey, you can do select average of my var from my table. Or if you want to have the data, the final result, this average number on your computer, so you can put it on a chart or whatever, then you can simply execute this, right? Okay, presentation done. No, kidding. This almost looks like cheating, right? Because, I mean, I didn't really change that much and I had these three big problems here. So why don't I have those problems down here, right? Let's look at how the system works under the hood to understand why those problems don't occur then, okay? So this is the schematic illustration of the cluster that we have seen earlier. And again, so we have these many data nodes here, and let's say we have this data set from 75 gigabyte, just for illustrative purposes. And how would our server Spark Hadoop solution try to work with that? Well, first of all, the data would not be stored on simply one of these computers, right? So here, for example, it's split up across 3 different nodes. And each of those then is just 25 gigabytes. And side note, in such a system, actually, it wouldn't just be on replicated once, but it would be replicated many times. So that's the yellow boxes down here, right? So imagine you lose one of the servers, some physical problem with it, right? Anything that can break will break at some point. So even if that were to happen on such a distributed system, usually through replication, you would avoid any kind of data loss. Okay, so that's good. Now let's try to understand how it would compute the average that we were looking for. So remember, each of those data nodes is in and of itself just a server, right? So it has some hard disk, it has some memory and some CPU, and these numbers I just made up. So we have a nice example, okay? So how could we efficiently compute the mean in such a system? Well, I could start by just saying, well, let me read in this data here and compute the mean here. So now I have the mean of this first bit. And in a way, I could do the same thing here and here. And then I could simply compute the mean of the mean, right? So in a way, what I could do is I could divide and conquer these problems and break it into subproblems. Because here this should be possible. I need to be careful, right? So it has to have the same number of observations in each, but generally speaking, you get the idea. I could compute the mean here, could compute here, could compute here, could compute the overall mean. And now I could simply ask for this mean back to my computer, right? Okay, that actually seems like a good idea. Now let's think this through again. Did this really solve all those problems? What were the problems again? Okay, so 3 problems, right? Input, output, space complexity, and time complexity. So let's go through them one by one. What about input, output? So we mentioned if I do the select star, get all the data to my laptop and compute the mean there, the first problem is I have to download all this data to my computer, right? Is that problem solved? Well, the final step here, right? The just return this one number. Yeah, this is still has to go over the network to my computer, but it's just one number. So that's fine, right? But what about the big data? Is that moving a lot here? Well, let's have a look. Well, since I'm computing the mean of this first bit on the machine where it's actually stored, I actually don't have to do any kind of expensive network input output operation, right? I still have to read it in here. Yep, that's where it is. But I don't really have to move this entire block of data somewhere expensively across the network. Now, if for some reason this computer here was busy doing something else already, maybe I have to move this data and read it into this computer. But since those are connected and usually physically co-located in a way, this is still much faster than if you were to download it on your own computer. Okay, so input output actually is solved, which is nice. Now, what about space complexity? If I download all the data to my computer, I could have a problem, right? Because 75 gigabytes, I might not be able to really read that into my memory before it crashes. So what about the solution here? Well, since this is not 75, but just 25 gigabytes, which is what this machine has here, I can read it in just fine. So I won't have that problem either. And I won't have it neither here and neither here, right? Because all of those machines have just enough to read in the data. So that's great. We also solved the space complexity one. And now thirdly, what about time complexity? Well, time complexity in this example can basically be cut by 3, right? Because I can compute these submeans on the 3 nodes here and then just compute the overall mean. Now, in reality, you wouldn't have a 25 gigabyte data set here, but usually something between 128 megabytes and 256. So you could imagine if you have this data spread across dozens of worker nodes that you have available to yourself, then you could cut the time complexity by whatever number of nodes you have. Yeah? So you can speed that up considerably as well for anything that you can parallelize in a meaningful way. Okay, so that's great. We have solved the basic problem of it. So let's quickly recap. The core strategy is bring the computation to the data. Do not bring the data to the computation. Okay, I think if there's only one thing to take away from the presentation, it's probably this. The mindset that I usually try to have in my when I was working as an analyst in monetary policy was to say, okay, I want to use my ThinkPad only for the very final plotting step, right? Because for plotting, Excel can be nice sometimes, right? It's handy. You can give it to other people. Everyone can sort of fiddle around with it. But really, I just want to have the last step done there, and everything else I want it to be done somewhere server-centric, right? As soon as I do things server-centric, there are many things I don't have to worry about. Maybe it's an expensive computation, still takes long on the server. That's fine. I can shut down my ThinkPad. I come back tomorrow. Thing is running or is done. It's not happening on my laptop, so I don't have to worry about all these things, right? Of course, that does require you to have all your data available somewhere on your Hadoop or Spark cluster, right? And maybe you don't. So one of the first things that I did when I started working in monetary policy was to move a lot of the data that the division was still collecting locally in a way on a network drive to our Hadoop cluster. While luckily our statistics division already has moved most of the big data sets which we have there anyways, right? So now you have them in one place and you can quite easily merge them and do any kind of aggregation that you like with it. The other reasons to think about this, I would say, is this, these kind of technologies are really here to stay, right? I mean, I'm an economist by training myself, so I have to make a prediction, I guess. And I would say in 10 years, 15 years, 20 years, whatever exactly it might be, people will do fewer and fewer computations actually on their own computers and rather have some kind of workbench in the cloud that they use for their data analysis. Because it's just that capital if you think about it, right? If you buy an expensive laptop, maybe you use it 8 hours a day. PhD student, maybe you use it more. And the other 16 hours a day, it's just that capital. Why would you do that, right? It's not an efficient allocation of resources, really. So my best guess would be we move to some kind of a solution that looks more like this. Yeah, so you want to do all the expensive computation somewhere in those systems here. And basically always ask yourself, when you load a lot of data into your computer, do you really have to do that? Or is there any way to do it server-side? Okay, so one question that came in the other time I presented this was that what I've told you so far looks in a way just like a data warehouse solution that you might also get from Oracle or Microsoft SQL Server or whatever, right? And on the first sight, I would say yes. So both systems encourage you to do all the heavy lifting on that system rather than on your laptop. And that's a good thing, right? But I think as you look under the hood, Hadoop and Spark offer quite considerable advantages. So I've listed some of them here, and then in blue again, the ones, on blue against the ones that I find most important. So first of all, one thing that I never liked about these data warehouse solutions is that they are pretty much black box, right? If you ever work with Oracle Developer, you have these tables there and you can create new tables or whatever the case might be, but it's very difficult to interact with the actual data that's underlying the table, right? You only have this abstract representation. And in a way, everything is a table or a view, but it's not like you can really work with the files there. And the algorithms that are being used there, they're secret, right? I mean, parts of why these systems sell so well is because they are quite fast and they're not sharing this, right? And maybe most importantly, you don't have a file system available in these systems that you can anyway meaningfully interact with, right? Which is something that you have in a Spark Hadoop setup, and I'll show you in just a minute. So the second one is Spark is really the go-to solution for any kind of big data machine learning problem, right? We've seen that in the last presentation as well. And finally, the last one is meant as a bit of a joke, but you know, if these companies like Amazon, Facebook, Netflix, and Google all use this kind of technology, and you know, arguably they made billions and billions of money by extracting value from data, maybe there is something that we as economists can learn from them, right? Okay, so I will close, if you give me just another minute or two, by giving you just a short overview again on Hadoop and the file system that's behind it. So I wanted to do a live presentation using the ECB system, but I still have access to some confidential data sets, and I'm always paranoid about accidentally leaking something. So I'm afraid the screenshots will have to do. We have this lab here, which is just one schema in our Hadoop. That's publicly available to anyone in the bank, right? And people can just use it to play with it, which is a great thing to have. And you can imagine what happens. Of course, people post there all kinds of data and it's becoming a bit messy, but that's fine, right? So this part we have seen already. We can select something, look at something, but now let's look under the hood, right? What's hiding behind this airline one table? So you can actually go to a path that looks suspiciously like something on a network drive that you might have, right? And you can see actual files. Yeah, here's your parquet again, right? And you can, you can upload stuff here, you can delete stuff, you can interact with this file system just as if it was a local network drive. So let me do that just to show you, right? Imagine you have some huge table somewhere already on your Spark system that maybe your statistics division is providing, and you have some data locally that you maybe got from the web or from a course at a different institution, and you want to merge them, but doing that locally is too expensive. So what do you do? Well, here I just create some fake data, saving that data. This is still in my local computer, right? Saving this thing here locally. And then I can say, okay, let me go again to my Hadoop front web page here. Click on upload. I can upload the data set. Now I have it sitting here, right? And now I can write a little bit of SQL to create a table based on this. Okay, my table has been created. And now I can look at the data here in Huey. But more importantly, basically anyone that has access to this lab here in the ECB could now use this data to merge it with any kind of other data that's available on a Hadoop cluster. And if you think, well, okay, fair enough, but that was a bit cumbersome, of course, you can automate all these things, right? So there's a package that we wrote called connectors that if you do this.create table and you supply the data, you can give the path in the lab, it will simply do all of this under the hood for you, right? So you don't have to do these things manually. Okay, so I do have a quick tour through the Hadoop stack if you're interested, but also would be a good point to close and open for questions if there are any. I wasn't able to monitor the chat while I was speaking, but I'm sure someone can bring them to me.
Thank you. Let's see if we have questions.
One thing that if I want to install a cluster, you said only the professional people can do it. Like if I have a set of computers at home, is that difficult to set up a cluster?
Yes, I would not do that. Maybe there are some good instructions online, and I guess if you really want to learn under the hood how these things work, that might be a good exercise. But generally speaking, if you're an economist and your goal is to use these new technologies to efficiently produce research output, then you want to go with a managed service. And when I started doing this, I used something called Elastic MapReduce, which is basically a Amazon's version of this. Yeah. Today, I wouldn't even bother doing this because then again, there is like a, there's actually still a server that I need to log onto, and I have to use command line scripts to do some of the other things. And no, why would I do that, right? Today, you have things like Databricks, where you have a nice UI, you can click around. You have like Jupyter notebooks where you can write some Spark, and it's just much, much more convenient. So as a general note, I would outsource as much as that as possible, unless it's something that you think is fun doing, right?
Sorry, tiny question. I have confidential data from Statistics Portugal. Is it how can they keep my data confidential if I use those services like Databricks in the cloud?
Yeah, if in the cloud, that will likely be very difficult. So what I would do, I guess, in your case is first talk to your IT division. Maybe they already have something. So I know that the ECB is moving a lot of things to the cloud. Now there is these different level of confidentialities. I know they're not moving everything. So it depends a bit on what your data is. Maybe something is so highly privileged that you just cannot put it there, right? But I wouldn't fare with them whether any such system is already available, or maybe whether an on-premise one exists that you're not aware of.
Thank you. Any more questions? I do have a question. So you left with a teaser, a quick tour to the Adobe stack. Is there like a link or something anyone that wants to follow?
I don't know. It's just it's just the next slide, and in case there were no questions, so I had a bit more. I had a bit more material. But yeah, I mean, I'm happy to go through this if there are no other questions on the presentation itself. Or depending on how we're doing on the time, actually, I didn't follow through with it.
A question online, if you don't, which is it's from Sebastian Buhai is asking. So this seems to be mostly relevant for data providers, data management, that they should move to Hadoop Spark. Is that so?
Yeah, yes and no. So I think the first step is that if you work in central banking, let's say, I think the first step is that your IT division and your statistics division team up and say, okay, look, we have many very granular data sets in these institutions, like credit registers or security holding statistics, maybe even trade level data. And we just cannot store this as CSV files on some kind of network drive. This is last century stuff. We have to move that somewhere on a system like this. Yeah, that would be the first step. But then I think the second step, if you're more on the analyst economist end of a central bank, is for you to then not select star from table and download all of the data again, save it as a CSV, and then use your old Stata, RPython, MATLAB scripts to work with the data, right? So I think both ends have to move. Now, if in your institution no such cluster exists, then it might be quite difficult as an analyst or as an economist to start exploiting the benefits of that. We have seen some other presentations these 2 days, right, that showed what technologies are available to do some of that on your own laptop, and that I would raise can solve a lot of problems. On the other hand, I guess one has to admit that the hardware that is available to you is not irrelevant, right? Even if you use very efficient processing there, depending on the data size, you will run into some limits, and then you just need some kind of system set up for you, I would say.
Yeah, we do have another question online. But this is from Bernardo Costa. Do you have experience with Dask? If yes, do you recommend or is Spark better? And then there is a second question. I'll pose it now. So, do you recommend any course or resources for economists to get closer to data engineering?
Interesting. So on the first one with Dask, I have worked with it a little bit. I can't say what really in the end then made me stick to Spark is probably because within the institution Dask wasn't used that much and was just easier to communicate with everybody around using PySpark. But I mean, I originally when I checked it out, it seemed quite promising in terms of how quickly it's able to produce data. But I wouldn't know for sure. Then the second problem about good material to get into. So I think first of all, practice makes perfect. And what I would advise against is taking some class if you don't have any way then to apply it in your work, because then you tend to forget how this works, right? Now, assuming you have access to some kind of such system one way or the other, there are some good resources out there. I mean, nowadays the problem is more that there is just too many free resources even to be able to scan through them all and see what's useful. If the question is in the chat, maybe we can just take it up bilaterally, because I would have to look around a bit and I can't come up with anything on top of my head right now. But happy to follow up.
So I guess that's it. Thank you again, Yannick.
Thank you very much.
Well, we have come to an end. Let me just give you, just say a couple of things. First, that you will receive an email with a link for all the workshop materials. And we're going to also send a form where you can give your opinion about this workshop. I want to thank all our speakers. And they were kind enough to share their knowledge with us, and I think it was very important for everybody. I also want to thank the wonderful staff at BPLIM that made this possible, and in particular, Joanna, who behind the scenes made sure that everything worked fine. Okay, that's it.